Hello and welcome all of you for today's class. Well, in our previous classes we studied few things about the basics of strength of materials, the module 1, the stresses and strains, the Hooke's law, the Poisson's ratio, and a few other concepts we developed, and we solved some numerical problems also, and we did some derivation with respect to elongation of a tapering bar with circular and rectangular cross sections. And we also studied about the elongation that is taking place because of self-weight. Then towards the end of the previous class, I was talking about the compounder, the composite bars. A quick recap of that. A composite bar can be made of two bars of different materials. They are rigidly fixed together so that both bars strain together under external load. So this becomes the major, this becomes the fundamental what I should say principle on which we try to find out the stresses. So as the strains in the two bars are same, the stresses in the two bars will be different, and they depend on their respective modulus of elasticity. Generally, it can be concluded that a stiffer bar will share major part of the external load. So we were trying to derive an equation for the stresses in a composite bar. For example, we are having a solid rod, right, which is placed inside a hollow tube. So let's consider a composite bar consisting of a solid bar of diameter d, completely encased in a hollow tube of outer diameter d and inner diameter d, subjected to a tensile force P. Now let the extension of the bar of length of the composite bar of length L be delta L. Let ES and EH be the respective modulus of elasticity of solid bar and hollow tube respectively. Let sigma S and sigma H be the stresses developed in the solid bar and the hollow bar. So particularly pay attention to what I have written here, that is, since change in length of solid bar is equal to the change in length of the hollow tube, we can establish the relation between stresses in the solid bar and hollow tube as follows. So change in length in the solid, sigma S L by ES, is equal to change in length of the hollow tube, that is sigma H into L divided by EH. Then we try to modify this equation. In fact, this will be the fundamental equation which connects the stress in solid bar to the stress in the hollow tube in terms of the modulus of elasticity of the solid bar and the hollow tube, area of cross sections of the hollow tube, solid bar. Then we know that the total load is to be carried both by the solid tube as well as solid bar as well as the hollow tube. So we put sigma S ES, stress multiplied by area, stress multiplied by area. This is for the solid portion, this is for the hollow portion. Then substitute this value of sigma S into this equation. Then finally we arrive at an equation like P is equal to sigma H AH plus ES by EH into AS. ES by EH is called the modular ratio, which I was telling in the last class. Sometimes in problems they may give you separately values of ES and EH, or otherwise they may directly say the modular ratio is so much, like 8, 10, 12, 15. Using the above equation, stress in the hollow tube can be calculated. So once you know the stress in the hollow tube, I will put it here, then I will calculate what is the stress that we are getting in the solid bar. So let us try to work out a numerical example. So a flat bar of steel 24 mm wide and 6 mm thick. So this is 24 mm wide, right, and this is the solid bar 6 mm thick, is placed between two aluminum alloy flats 24 mm by 9 mm each. This is 9 mm, this is 9 mm. These are aluminum alloy flats, and this is a steel solid bar. Totally it becomes 24 by 24. The three flats are fastened together at their ends like this, so that they undergo equal expansion. An axial tensile load of 20 kilonewton is applied to the composite bar. I am applying a force of 20 kilonewtons here. You are asked to find out what are the stresses developed in steel and aluminum alloy. Assume ES is equal to 210,000 MPa and EA is equal to 70,000 MPa. So how do we solve such problems? We have developed the basic equations. So we will try to work this problem based on the previous derivations whatever I told. So, to summarize, we have two aluminum alloy flats. In between we are having a solid bar or a solid flat. The dimensions are given. The axial load that is applied is about 20 kilonewtons. This is also given. ES they have given, and E for EA, that is for the aluminum, also they have given. We have to find out what is the stress that is developed in the aluminum flat as well as in the steel flat. Let us find out. Area of the steel flat, AS is 24 by 6, so it is 144 mm squared. Area of aluminum alloy flats, AA, each is 24 into 9. We have two flats, so 2 into 24 into 9, so you will be getting 432 mm squared. Now, since all the flats elongate by the same extent, we have the condition that stress in steel, length divided by modulus of elasticity of steel, this will give me the elongation. This should be equal to stress in the aluminum multiplied by the same length divided by the modulus of elasticity of aluminum flat. So, using this equation, we establish the equation that sigma s is equal to sigma a into ES by EA. We know that ES in the problem they have given it as 210,000, aluminum they have given 70,000. So, 210,000 divided by 70,000 will give you 3 times sigma a. So, stress in steel sigma s will be equal to 3 times the stress in aluminum. Now, we will put, since P is equal to PS plus PA, so load carried by the steel flat PS is equal to sigma s into AS, load carried by aluminum is equal to sigma A into area of the aluminum flats. So, this can be written as, we know that sigma s is equal to 3 times sigma A, so I will put P is equal to 3 times sigma A AS plus sigma A plus AA. I will try to simplify this. We will write it as sigma A is equal to 3 times AS plus AA, that is area of the aluminum, from which I will calculate what is the stress in the aluminum. So, sigma A will be equal to P divided by 3 AS plus AA. The load is given as 20 kilonewtons, so I will convert it into newtons, 20 into 1000. Area of steel, that is given as, we have computed, it is 144, aluminum is 432. Just substitute in this equation, you will get stress in aluminum as 23.15 MPa. Once we know this, we know the relation between stress in steel to stress in the aluminum flat as 3 times this. So, sigma s should be equal to 3 times this value, which will be equal to 69.45 MPa. Like this, we try to work out the stresses that are generated, that are produced in compound bars, which are made up of 2 different materials. Okay, let us look into another type of a problem. See, a short post is made by welding steel plates into a square section. These are the steel plates. They are welded together so as to form a square section. The dimension is 200 mm. This is also 200 mm. And then it is filled inside with concrete. The side of the square is 200 mm and the thickness T equals 10 mm as shown in the figure. So, the thickness of the steel plates, whatever we are using it, is about 10 mm. The steel has an allowable stress of 140 Newton per mm squared. So, in the previous class I told you that we have a concept of what is called factor of safety. So, based on the factor of safety and the yield strength or the ultimate strength of the material, they have worked out and they are giving that you cannot exceed the stress in steel to be more than 140 Newton per mm squared. What do we mean by this? The steel has an allowable stress of 140 Newton per mm squared. Means the stress in steel should not be more than 140. And the concrete has an allowable stress of 12 Newton per mm squared. That means stress in steel should not be more than 140. Stress in concrete should not be more than 12. Now they say determine the allowable safe compressive load on the post. EC, that is modulus of elasticity of concrete, is given as 20 GPa, then modulus of elasticity of steel is given as 200 GPa. See, in this problem it is a reverse type. Given the load, we will find out what is the stress in steel or the stress in concrete. Now, the problem is framed in such a way that you have to determine what is the allowable safe compressive load that this post can carry, such that the stress in steel is not more than 140 Newton per mm squared, and stress in steel the stress in steel is not more than 140 and stress in concrete is not more than 12 Newton per mm squared. So, we will try to solve this problem using some logic. Okay, first, since the composite post is subjected to compressive load, both concrete and steel tube will shorten by the same extent. Using this condition, following relation between stresses in concrete and steel can be established. Same way, sigma s is equal to sigma c multiplied by Es divided by Ec. This is nothing but the modular ratio. Now, we will assume that we are applying some load such that stress in steel is equal to 140 Newton per mm squared. We will assume that some load is applied such that stress in steel is limited to 140 Newton per mm squared. So, for this load, if stress in steel is limited to this, let us work out what would be the stress in concrete using this relation. So, 140 equal to sigma c, this is 200 and this is 20 they have given. So, I can work out sigma c to be equal to 14, sigma c works out as 14 Newton per mm squared, but they say that it should not be greater than 12. So, because this is becoming greater than 12, this load cannot act. With this load, the stress in steel may be 140, whereas the stress in concrete exceeds 12 Newton per mm squared. Therefore, this load cannot be the safe load. We will conclude like this. Hence, the assumed load is not a safe load. Now, let us look into the next alternative. Instead, let us assume that the load is such that sigma c is 12 Newton per mm squared, because this is the maximum allowable limit. Using the same relation, I will work out the stress in steel, which is 120. Fine, this is less than 140 Newton per mm squared. Therefore, what should be the assumed safe load? The safe load should be such that stress in concrete is limited to 12. If we limit the stress in concrete to 12, the stress in steel will be 120, which is less than 140. This is also not exceeded, this is also not exceeded. Therefore, the load is a safe load. Like this, we will establish the condition. Based on this condition, let us work out like this. Well, what is area of concrete section? We can work it out as 180 by 180, which is 32,400 mm squared. Area of the steel tube, for the outer dimensions 200 by 200 minus you remove this concrete area, I will get 7,600 mm squared. Then we will put P is equal to sigma c AC plus sigma s into AS. Sigma c I will take it as 12 into area of concrete section 32,400. Stress in steel now would be 120. I will take this value. Stress in steel tube is 7,600. We will simplify this. You will be getting the load as 1300.8 kilonewtons. So, this is the load that the steel post, that composite post can carry, such that the stress in steel is 120 Newton per mm squared and stress in concrete is 12 Newton per mm squared. See, like this, depending with using the same set of equations, because we are having different types of problems, mainly with respect to either given the load, find out the stresses, or given the stresses, find out the load. Like this, you can have varieties of problems. Next, we solved about two problems today. In the seventh problem, it was mainly with respect to some two bars, two aluminum flats with one solid bar, that is a steel solid bar. We found out what is the stress in steel, stress in aluminum. In the second problem, it was a sort of an encased section, what I can say. We are having a steel tube outside, then inside we put concrete, and now we are going to calculate what is the safe load such that the stresses in concrete and steel are not exceeded. Now, another type of a composite system is like this. I will read this problem. A rigid bar is suspended from two wires. See, this is a rigid bar and this is suspended from two wires. One of steel, this is a steel wire, and the other is copper. The length of the wire is 1.2 meters. Length of the wire is 1.2 and the diameter of each is 2.5 mm. Both steel wire and the copper wire both are 2.5 mm in diameter, length is 1.2 meters and both of them are supporting or holding this rigid bar. Now, a load of 500 newtons is suspended on the rigid bar such that the rigid bar remains horizontal. Now, we are applying a load 500 newtons. The load is applied in such a way that this bar does not rotate, means it remains horizontal. Next, if the distance between the wires is 150, this distance is given as 150, distance between the wires. Determine the location of the line of application of the load, means where this load should be placed or where this load should be applied on the rigid bar such that this bar, rigid bar, remains horizontal. It does not rotate like this. So, determine the location of line of application of the load, means you should find out x. Next, what are the stresses in each wire? What is the stress in steel and stress in the steel wire and stress in the copper wire? And by how much distance the rigid bar comes down. Because of this, there will be elongation. Because of this elongation, the rigid bar will be coming down. Given ES is equal to 3 times ECU, that is modulus of elasticity of the steel wire is 3 times the modulus of elasticity of the copper wires, and it is given as 20100 Newton per mm squared. So, we will again try to understand this problem. A rigid bar is suspended from 2 wires, one of steel and the other of copper. Length of the wire is 1.2 meters and the diameter of each is 2.5 mm. A load of 500 newtons is applied on the rigid bar such that the rigid bar remains horizontal. If the distance between the wires is 150 mm, determine the location of line of application of the load, means you should find out the value of x measured from, say, this particular point, measured from the steel wire, where this load should be placed such that the bar remains horizontal. Next, what are the stresses in each wire? What is the stress in steel wire? What is the stress in the copper wire? And how much distance the rigid bar comes down, given ES is equal to 3 times ECU as this particular value. Now, how do we proceed with this? First is that the bar should remain horizontal. If the bar should remain horizontal, elongation in steel wire should be equal to elongation in the copper wire. We use this as the compatibility condition. See, if the 2 wires undergo different elongations or different extensions, then obviously the bar will rotate. Because now they have mentioned that you should apply the load or balance the load such that both the wires elongate by the same extent, and if they undergo uniform elongation, the rigid bar AB will remain horizontal. So, we use that as the condition. Okay. First, we will start with this. Area of the copper wire is equal to area of the steel wire, which is pi d squared by 4. We get it as 4.91 mm squared. Now, for the rigid bar to be horizontal, elongation of both the wires must be the same. This condition leads to the following relationship between stresses in steel and copper wires, as sigma s would be equal to ES by ECU times sigma CU. ES by ECU they have given it as 3. So, we will establish the relation that sigma s is equal to 3 times sigma CU. This is based on the condition that the rigid bar will be horizontal and elongation of both the wires will be the same. Using this condition, we establish this. Next, we will go for force equilibrium. Using force equilibrium, the stresses in copper and steel wire can be calculated as total load P, load carried by steel wire plus load carried by copper wire, sigma s AS, sigma CU ACU, simple. Load is equal to stress multiplied by sectional area. We know sigma s is equal to 3 times sigma CU. So, 3 sigma CU AS plus sigma CU ACU, simplify it, you will get it as sigma CU into 3 AS plus ACU. So, I will work out the stress in the copper wire. So, stress in the copper wire would be equal to P divided by ACU plus 3 times AS. We will make all these numerical substitutions for the load ACU AS. I will be getting the stress in the copper wire as 25.46 MPa. Using this relation that stress in steel wire is 3 times the stress in the copper wire, I will get the stress in the steel wire as 76.37 MPa. See, both the wires have undergone same elongation, but they are subjected to different stresses. Copper wire is subjected to less stress, then steel wire is subjected to more stress. Then what is the downward movement of the rigid bar? See, downward movement of the rigid bar will be equal to the elongation of the wires. So, you can use anything. I will use steel. Delta Ls is equal to sigma s by Es times L. So, the stress in steel we got it as 76.37. Modulus of elasticity of steel is given. Length is 1.2 meter, that is 1200 mm. I will get this value as 0.456 mm. Means the rigid bar will move down by about 0.456 mm. The last point that we have to find out is the position of the load on the rigid bar. The position of the load on the rigid bar is computed by equating moments of forces carried by steel and copper wires about the point of application of load on the rigid bar. This is the condition that we are going to use. Because the rigid bar has not rotated, now we are having load carried by the steel wire, load carried by the copper wire. If you take the moment of both these forces about the point of application of load, both of them should generate same moment but opposite directions. See, one is like this, one is like this. About this point, if I apply this force about this point, gives a moment in the anti-clockwise direction. This force about this point gives a moment in the clockwise direction. One tries to rotate anti-clockwise, other one pulls it back in the clockwise direction, so that it will not rotate. So, Ps into x is equal to Pc into 150 minus x. Let us go back to this problem, to the sketch. See, this is the force carried by steel. I will say Ps times x, it should be equal to Pcu times 150 minus x. So, load by this distance should be equal to this load multiplied by this distance. That is the moment I am considering. So, if we substitute all these values, whatever we have done, stress in steel multiplied by area of steel into x, stress in copper multiplied by area of copper into this distance, we try to simplify it like this, and we will get x as 37.47 mm from steel wire. So, if the load is suspended closer to the steel wire, because it is only 37.47 mm from the steel wires, if we suspend the load closer to the steel wire, obviously both the wires will undergo same elongation, as a result of which the bar remains horizontal. Suppose you suspend this load at the center, then what would have happened? Obviously, the moments would not have been balanced out. The load carried by steel, load carried by copper, the load and multiplied by these lever arm distances will change, as a result of which unbalanced moment will be there, and because of that unbalanced moment, what will happen is your bar instead of remaining horizontal, it may rotate like this or it may rotate like this. So, this is the problem which will illustrate the concept of the composite bar. Now, let us try to note few important points. If the load is suspended at the center of the rigid bar, then both steel and copper wire will carry the same load. Hence, the stresses in the wires is also same. As the moduli of elasticity of wires are different, strains in the wire will be different. This results in unequal elongation of wires, causing the rigid bar to rotate by some magnitude. So, that is the main problem for us. This can be prevented by offsetting the load, or with wires having different lengths, or with different diameter, such that elongation of wires will be the same. Suppose you want to apply the load at the center, still the bar should not rotate, means then one of the option would be to offset the load, or you can have wires of different lengths, right, or you can have wires of different diameter, such that the elongation of wires will be same. Based on this, you can expect different types of problems. Now, let us go to another example. A load of 2 meganewtons is applied in a column 500 mm by 500 mm. The column is reinforced with 4 steel bars of 12 mm dia, 1 in each corner. Find the stresses in concrete and steel bar. ES is equal to 2.1 into 10 power 5 and EC is equal to 1.4 into 10 power 4. So, we are applying a load of 2 meganewtons. This is applied on a column 500 by 500 and the column is reinforced with 4 steel bars of 12 mm dia, 1 in each corner. Find the stresses in concrete and the steel bar. ES is this, EC is this. This problem is fairly simple, not complicated as the previous one. Area of steel bars, AS. We are having 4 bars, then the bar diameter is 12 mm. So, 4 into pi into 12 square divided by 4. So, we will get 452.4 mm squared. Area of concrete, it is 500 by 500 minus whatever the steel area. So, this will be the area of concrete. Then we can establish the relation between stress in steel and concrete. Sigma S is equal to ES by EC times sigma C. So, putting all these things, we will get this as stress in steel would be equal to 15 times the stress in concrete. Then use this relation, P is equal to load carried by steel plus load carried by concrete. So, load carried by steel, I will write it as sigma S ES, load carried by concrete sigma C AC. Substitute sigma S is equal to 15 times sigma C and get one equation like this. P is equal to sigma C 15 AS plus AC. Using this, I can find out the stress in concrete. Stress in concrete sigma C would be equal to P divided by 15 P divided by AC plus 15 AS. Make all these substitutions, then you will be getting this particular value as 7.8 MPa. This is the stress in concrete. Then stress in steel sigma S would be equal to 15 times sigma C. So, we know this value, we know this the relation. I will be getting the stress in steel as 117 MPa. So, here in this particular topic, basically I have tried to give you some concepts with respect to the composite bars. Different types of problems I have tried to solve. All these things, they all come from the same concept that deformation in both the bars should be the same. So, here flat steel bar, right, sandwiched between 2 aluminum flats. Next, this is a steel tube, inside we have got concrete. Next, in this problem we are having a rigid bar which is being supported, one by steel rod, steel wire, another by a copper wire, and we want that this bar should remain horizontal under this particular load. So, at what distance the load should be placed such that both these bars undergo same elongations, and then how much they will elongate, then what are the forces that are carried by the steel wire as well as the copper wire. All those problems, all those information or how to find out those quantities I have demonstrated in this example. Then I have given you some note, like if the load is suspended at the center, what is going to happen. Then if you want to be applying the load at the center, then either you need to change the diameter of the wires or you need to change the length of the wires such that the bar remains horizontal. Then in this particular problem, we are applying a RC column, it is 500 by 500 mm with 4 corner rods. Next, the column is reinforced with this. So, in this case, how to find out the stress in concrete and the steel bar. So, these are some of the examples which will help you in understanding the stress analysis, the stress and strains that are induced in composite bars. Next, let us pass on to another concept or another requirement, that is what is called temperature stresses in a single bar. See, so far we are thinking of stresses and strains that are produced due to the external application of the load. Either it may be subjected to tension or it may be subjected to compression. Now we are getting into a situation wherein that external forces are not acting, but the variation in temperature. We will generally have some ambient temperature, Next, the temperature increases, then towards evening, towards night times it decreases. And moreover, sometimes it may happen that the seasons may also change. So sometimes it has been observed that the variation in temperature causes stresses in the bars. So how to find out such stresses? See, if a bar is held between two unyielding rigid supports, please focus on this concept. If a bar is held between two unyielding rigid supports, means supports are very strong, they do not yield, they are very rigid. And if the temperature of the bar is raised, what will happen? Then a compressive stress is developed in the bar as its free thermal expansion is prevented by the rigid supports. So you are having one bar without any rigid supports and other things. You try to increase the temperature, then simply the bar is going to expand. But if you prevent this expansion, suppose this was the length, because of the rise in temperature there is an increase in length. Suppose you do not allow this increase in length to happen, and it is held between two rigid supports, and the supports are so strong that it will not allow the bar to increase in length, then what is it going to happen? Bar wants to elongate. Supports are preventing them. As a result of which, bar would like to elongate, but the supports are not allowing it, means the supports are generating a compressive force on the bar, resulting in a compressive stress. So if the temperature rises, then a compressive stress is developed in the bar as its free thermal expansion is prevented by the rigid supports. Similarly, if the temperature is reduced, then a tensile stress is developed in the bar as its free thermal contraction is prevented by the rigid supports. So this is a very interesting concept. You will have a lot of applications in engineering. Sometimes even in buildings, when we are designing it, if the length of the building is more, or if the buildings are highly angular in nature, like it is not in one line, right, it is all going in different angles, then to see that cracks do not form, right, we are going to leave what are called the expansion gaps, so that within that the expansion, the free expansion and contraction can take place, so that these stresses are not generated. So if a bar is held between two unyielding rigid supports and its temperature is raised, then a compressive stress is developed in the bar as its free thermal expansion is prevented by the rigid supports. Similarly, if its temperature is reduced, then a tensile stress is developed in the bar as its free thermal contraction is prevented by the rigid supports. Please note this point. The bar can buckle due to large compressive forces generated in the bar due to temperature increase. Suddenly, you may find that originally the bar was straight, right, but over a period of time it has buckled. That is because of the large compressive forces that are generated in the bar due to temperature increase, or may fracture due to large tensile forces generated due to temperature decrease. So try to understand this particular concept. If you increase the temperature, if you prevent the free expansion, then compressive forces are generated. If you decrease the temperature, you are preventing free thermal contraction, as a result of which tensile forces are generated. So under compressive forces, the bar can buckle, under tensile forces it can fracture. So temperature stresses are of considerable importance in engineering. Now let us consider a bar of diameter d and length L rigidly held between two supports as shown in the following figure. Okay. This is a fixed end, very rigid support. This is also a rigid support, means the support is like this, a huge one you can imagine, so that this will not allow this to move. Similarly, this support is very huge like this, again it will not allow this rod to move in this direction. That is what we mean by rigid supports, means they do not undergo any deformation. Now L is the length of the bar E is the modulus of elasticity, say maybe some d is the diameter or whatever it is, and alpha is the coefficient of thermal expansion, that is linear expansion or contraction. So, let alpha be the coefficient of linear expansion of the bar, and its temperature is raised by delta T degree centigrade or delta T Celsius. So, bar is length L held between two fixed ends, alpha is the coefficient of linear expansion, and temperature rise is delta T. What is the free expansion of the bar? The bar would like to expand by an amount equal to alpha, that is linear expansion, temperature rise delta T multiplied by length L. Bar would like to expand so much by alpha delta T L. Now, this equation is very nice to look at it. If you want to reduce this, you may not have much control over change in temperature, but if you can be using materials which have low thermal coefficient of thermal expansion, then for the same temperature increase, the thermal expansion will be less. Or if you reduce the length of the bar for the same material, for the same temperature increase, the free thermal expansion of the bar can be reduced. These are of very practical importance. Now, since the supports are rigid, the final length of the bar does not change. Bar would like to expand, but supports are preventing them, so the final length of the bar does not change. That means the fixed ends exert compressive force on the bar so as to cause shortening of the bar by alpha delta T L. This likes to expand so much, but the supports do not prevent them. So, what they are in turn doing it, they are compressing the bar. If the bar would like to expand by 2 mm, the compressive forces generated by the supports will be such that it is going to compress the bar by 2 mm, as a result of which the final length of the bar does not change. So, therefore, what is the compressive strain in the bar? This is the change in length divided by the original length. So, we will get alpha times delta T. Once you know the strain within the elastic limit using Hooke's law, I can find out compressive stress as equal to alpha times delta T E. So, we start from free thermal expansion of the bar alpha delta T L. Supports are rigid, so the final length of the bar does not change. Therefore, the fixed ends of the supports exert a compressive force in the bar so as to cause shortening of the bar by this so much. Hence, the compressive strain in the bar is change in length divided by the original length, that is alpha times delta T. Once you know the strain in the bar, you can find out the stress as alpha delta T times E. Hence, thermal stresses introduced in the bar would be equal to alpha times delta T E. Now, let us try to work out a problem on this. A rail line is laid at an ambient temperature of 30 degrees Celsius. Means whenever the rail line is laid, the atmospheric temperature was 30 degrees centigrade. The rails are 30 meters long and they have left a clearance of 5 mm between the rails. So, you know that you are having long rails, you would have seen that sometimes after some length they will be leaving a clearance. The clearance is about 5 mm between the rails. Now, if the temperature of the rail rises to 60 degrees centigrade, then what is the stress developed in the rails? Assume alpha to be so much and modulus of elasticity as this. Let us work it out. The length of the rail line is given as 30 meters, so it is 30,000 mm. Alpha, I am taking this value. The temperature rise. See, the rail line was laid at 30 degrees. Means that we will consider it as the normal temperature, beyond which the temperature rises to 60 degrees. That means the temperature rise delta T is equal to 60 minus 30. So, the rise in temperature is about 30 degrees Celsius. Now, what is the free expansion of the rails? It is alpha delta T L. We know alpha, we know delta T, we know L. So, this would be equal to 10.35 mm. means the rail would like to expand by 10.35 mm. But this thermal expansion, right, prevented by the rails. It would like to expand by 10.35 and we have left a clearance of 5 mm. That means it can happily extend by 5 mm. Afterwards it cannot extend because it is going to be supported by the another long line of the rail. So therefore, the thermal expansion that is prevented by the rails is free expansion is 10.35, clearance what we have left is 5 mm. So therefore, how much of expansion we are preventing? It is 5.35 mm. Suppose we had left the clearance as 10.35 mm, then the thermal expansion prevented by the rails would have been 0. If the thermal expansion prevented by the rails is 0, then the strain would be 0. If the strain is 0, then stresses would not have been developed at all. But 10.35 mm we cannot leave. For some practical purposes, we will say that only we can allow up to 5 mm. So that means we are preventing the rail from its free expansion of 10.35 mm to only 5.35 mm, means we are restricting it. And this restriction is caused by applying the compressive forces from the ends. So what is the strain in the rails then? 5.35 divided by the length, so this would be the strain in the rails. Then the compressive stress in the rail is this strain multiplied by modulus of elasticity. Look at this value. The strain is, the stress is 37.45 Newton per mm squared or MPa. So that means suppose we had not left any clearance at all, then this would have been more. If this is more, the strain would have been more. If the strain is more, then the stress also would have been more. So approximately, just for our understanding purpose, we will just say that if we had not given any clearance, then the thermal expansion prevented by the rails would have been twice this quantity. The strain would have been twice. If the strain is twice, the stress would have been also twice. So instead of 37.45, probably you would have got close to about 75 Newton per mm squared. So this is of a very, very practical importance. In various instances, right, we use this particular concept and we do our engineering in such a way that the stresses that are produced are within some permissible limits. So that is with respect to temperature stresses in a single bar. Now the temperature stresses will be also there in a composite bar. So just like the stresses and strain that are produced due to mechanical loads or external loads in a single bar and a composite bar, same way we are studying the temperature stresses that are produced in a single bar and temperature stresses that are produced in a composite bar. So how do we calculate it? See, again, a composite bar is made up of two bars of different materials perfectly joined together, so that during temperature change both the bars expand or contract by the same amount. They cannot undergo differential expansion or contraction. Uniform expansion and contraction will be there in the composite bar. But what is happening, since the coefficient of expansion of the two bars is different, thermal stresses are developed in both the bars. Now consider a composite bar of different materials with coefficient of expansion and modulus of elasticity as alpha 1 E1, alpha 2 E2. We are having two bars of different material. So therefore, the coefficient of expansion, the linear expansion and the modulus of elasticity, we will call it as alpha 1 E1 for bar 1 and alpha 2 E2 for bar 2, like this. Now let the temperature of the bar is raised by delta T, and we will assume that alpha 1 is greater than alpha 2. See, if alpha 1 is greater than alpha 2, the first bar would like to elongate, the free expansion of bar 1 will be more, free expansion of bar 2 will be less, but both the bars should undergo same expansion. One is trying to elongate more, another one is trying to elongate less, but both should undergo same elongation, as a result of which what will happen? The lower bar, that is the bar which is undergoing less expansion, will prevent the upper bar, that is bar 1, from undergoing more expansion, means it will pull it back, but the upper bar or the bar 1 which is undergoing more expansion will try to pull the lower bar. So, that means what is going to happen is mutually they interact with each other. For example, this tries to pull this tries to pull it, this tries to pull in the front, whereas this bar will try to pull this in this direction, this bar will try to push it back in this direction. As a result of pull and push that is going to take place between the two bars, they undergo a uniform expansion of say delta L. So, please try to understand this point. If you are having two composite bars with different material alpha 1 and alpha 2, to start the discussion I will assume that alpha 1 is greater than alpha 2. So, this undergoes more expansion, this undergoes less expansion, but such differential expansions are not possible. Both the bar should expand by same amount, as a result of which what we will do, the bar which is elongating more is pulled back by the lower bar, the bar which is elongating less is being pushed or is being pulled towards the front, right, by the upper bar, so that both of them will undergo uniform expansion. So, as a result of which different types of stresses will be produced. So, the bar 1 will undergo one type of stress, bar 2 will undergo another type of stress. As a result of which this may be subjected to compression, this may be subjected to tension, or vice versa reverse. This all depends upon which is greater, whether alpha 1 is greater than alpha 2 or alpha 1 is less than alpha 2. Okay, what we will do it is, we will stop at this particular stage, and then the next class I will try to continue with the development of these equations, and we will try to solve the problems. So, before I conclude, today the topic was mainly with respect to compound bars, different types of problems I illustrated how to solve them. So, the basic thing that we are going to use is that we say that the elongation should be same. For the elongation to be the same, using that condition we establish relation between two, that is bars of two different materials, like sigma s is equal to, right, Es by Ea times, right, sigma A. That is, we say that the stress in one bar is modular ratio times the stress in the other bar. We use that particular condition and we solved some different types of problems, wherein we were able to find out, understand many new interesting things. Another one was with respect to the temperature stresses. First, we have developed with respect to a single bar. So, we find that if there is a temperature rise, a compressive stress is produced. If there is a temperature fall, a tensile stress is produced. Because of the compressive stresses, the bar can buckle, and because of the tensile stresses, the bars may fracture. Hence, they are of very, very practical importance. See, it may so happen that you might not have applied any load, but one fine day, either in the morning or somewhere in the evening time, you may find that either the bar has buckled or the bar has fractured. Even without applying the load, failure can take place because of temperature variations. Well, in such a case, for a single bar, we determine that the free thermal expansion of the bar is alpha delta L. Then this is the contraction that is going to be generated. So, this is the strain, alpha times delta T. Once you know strain, I can find out the stress, alpha times delta T into E. Then I try to work out a problem wherein the free expansion was 10.35, out of which we allow only 5 mm to expand. We restrict this much of expansion. Because of this restriction, we have found out what is the strain in the rails. So, what is the compressive strain, and once we know the compressive strain, we will find out the compressive stress as strain multiplied by modulus of elasticity, and started with this temperature in a composite bar. So, I will conclude at this particular stage. In the next class, I will complete whatever the essential portions that we need to do in this. Okay, thank you.